Okay, then I would say let's start our second online training for students. I want to welcome you to this training. Thank you for attending. So for those who don't know me, I am Daniel. I will be today the presenter and moderator of this training. I am responsible here at Dlubal for our German team, so especially human resources, and I am also responsible for the marketing, especially for the e-learning and video marketing. I like that very much, and also next to that I do also some customer support, especially mail support. Good, I'm not alone. I do this training together with my colleague Ismail. Ismail, maybe you could say some words.
Hey, how y'all doing? Yeah, I'm Ismail. I'm in the marketing team here in Munich. I'm very honored to be here with you, Daniel, today. Yeah, I'm in charge of, well, making videos, e-learning videos, making RFEM models, and showing you guys the amazing features we have in our software. And just like you, I'm just so motivated to learn more and more about this software. And hopefully today you'll get to see just a little bit of what you can do with RFEM and RSTEP.
Excellent. So Ismail will be also here, the second voice, together with me. He will answer you almost every question, so we will try to help you as good as possible. And yeah, then I would say let's jump to the platform, go to webinar. Maybe for those who have already attended the first part of this training, few words to the platform. You can show or hide your control panel with the arrow here on the left upper corner. Then on the right side here, you can adjust your audio settings. So for those who can't listen us, please prove your microphone and your headphones. And if you have any questions, just enter here and Ismail will try to answer you the questions as good as possible. And after every chapter, we will also take a review of all the questions which could be important to answer and to show in the program directly. Yeah, what's the content of this training today? First of all, we start with an easy example. In this case, on the right side, you see this 2D frame with an hinged column. It's from a manual of RS Buck. We will model it, and then we put all the loads, calculate it, take a look to the internal forces, and then also to two buckling forms, buckling shapes. And then we continue with that concrete example of this concrete building. We put also loads there, calculated. You will get an introduction to load combinations, result combinations, and yeah, and then I think we have this training. Good. I will close my webcam that you can see more. And I jump right into RFEM. And now it would be interesting who of the attendees have already participated in the first part. So I have prepared a poll for you. Please answer me that poll. That would be very nice. Okay, the most of you have chosen, so I will close the poll, show you the results. And okay, interesting. So the most of you haven't participated in the first training. Doesn't matter. I think you will also learn something today, and you can watch the first part also on YouTube and on our website. And so it's quite interesting, but I think for everybody is here something to learn, something new. So let's start with the example. So I have here my manual of RSBuck. RSBuck is a program for buckling analysis, stability analysis, just for R-step, but you can calculate every R-step example also with RFEM. So here you see the example. It's a frame with a hinge column with some point and member loads. We will design and model here this frame. Yeah, we have here also some hinged members, hinged columns, also this bracing here. And then we calculate it, take a look to the internal forces, especially the bending moments here at the member hinges, because we suppose that they are 0. And then also take a look to the buckling shapes here, and also to the critical load. Okay, so let's do it. So when you open RFEM, then you see here this new window, general data. You can insert any model name. I will decide here for my pencil 2D frame. And because it's a 2D frame, I decide also to do that type of model in 2D exact, because I just want to activate vertical and horizontal forces in one plane, and also only one moment, my in this case, and only vertical and horizontal deformation, and no deformation out of the plane. This is important for that type of model. You can here decide also to change here the project folder. I decide here to take downloads because then I know where it is. You can change it, of course, or you can create a new project. It's up to you. And we don't need any classification of load cases and combinations. This is important for the next example we do 1 hour later. Yeah, my positive orientation of the global z-axis is downward. Yeah, and especially for you as international attendees, I can recommend you also open these units and decimal places. If we have someone from the American States, you can change here also the units, maybe from lengths to inches, feet, yards, and so on. This is maybe interesting to know. Other things like forces also to this one, per feet and so on. Good. Also here for loads, results, and so on. Good. Click OK. The new work window opens, and we start right now. So first of all, we create a new cross section. In order to create a new cross section, I can click easily here on the symbol bar, click here on new single member, and now let us create a new cross section, in this case an HEA 180. It's a very common use profile here in Europe, especially here in Germany. So click here on create new cross section for member start. And here you can see the most used and common used cross sections for steel. So I click here on HEA 180. Material is here, in this case, steel S235. When somebody doesn't see it, no problem. You can easily add it here in the material or create a new material. For instance, like here, I create here a new material, import from my material library. I set my filters for the metal, steel, and according to the standard, in this case, I decide for the Eurocode standard. And yeah, of course, steel S235. What does it mean? We have a yield strength of 23.5 kilonewton per square centimeter. I click here on OK. Or I can also click here on cancel because my material is already chosen correctly. So I can click here on OK. Again on OK. OK. And now I click here from the beginning. And I have also to activate snap to grids. Yeah, this wasn't activated now. So I have activated it. And then I draw my column 9 meters high. So the set coordinate is -9. And with a right click, I close this function. Okay, now another way of inserting this column also on the right side, because we have the next column with a distance of 8 meters. So I click here on new single member again. The already created cross-section RFEM, remember, and then just click here on OK. Within a distance of x equals 8 meters, we create the right column. Just click here on this grid. And then I want to show you another option of inserting this column or member in this case, is that you don't have to set here your column to the height of 9 meters. You can also choose another grid, and vertical to that, you can enter now the length, in this case 9 meters. You see it now on the right window, and then just press the enter or return button and the column will be there. Okay, nice. Okay, next step is creating here this upper girder. So therefore we create again a new cross section. So click here on new single member. Click here again on create new cross section. And click here on IPE 270. I choose here this one. Materials remains the same. Click here on OK. Again on OK. And then draw it from left to the right side. Okay, so upper girder is finished. Now let's create here this middle girder, or slab girder. For that, I create also a new cross section, but this time in a different way. In this case, with the help of the data navigator. With the data navigator, you have, first of all, an overview of all possible model objects, model datas, like nodes, lines, materials, and so on. Not only an overview, but also you can create inside this model data navigator also some new models or some new datas. So what we're gonna do is to create a new cross section. So I click here with the right click on the cross section. I click here on new cross section. And now I can also type here any cross-section description. And in this case, I type here IPE 360. And the program recognizes this automatically. The only thing you have to do is change the material from concrete to steel. Exactly. Good. I click here on OK. And now you can see here, when you open the tree structure, you can see here the created cross-section, IPE 360. And this is now blue. When you see something in the data navigator in a blue color, this means that this object isn't used so far. So in this case, we have created this cross-section, but no member has implemented this cross-section. So, and that's also the reason why it's blue. So we will see it when we create now a new member with that cross-section, and it will change from blue to this black color, because then we have used it for a member. So here in the middle, you want to create this middle girder, and it is at the height of 5 meters. So now we divide here this member at the height of 5 meters. So right click on the column here, right click, and go here to divide member. And now I have the possibility to divide any member with 3 options: graphically, intermediate nodes, or by distance. In this case, I choose distance. And now you see here the different arrows. And these arrows say to me that the starting node is here from down to upwards. Yeah. And for the upper girder, for example, the starting node is from on the left side, and the end node is on the right side. This is important to know where to divide your member. So in this case, I go from the button and 5 meters high. So I have to decide, okay, member start 5 meters. So it will divide my member here at the height of 5 meters. I click on OK. And this member was divided. And now we can do, because we have now this connection point here, now we can do and draw our middle girder here. So again, I do here new single member. Now, because we have already created here this new cross section, I only change here my member start, IPE 360. I click on OK, draw my middle beam from the left to the right side, perpendicular to my right column, and I click on OK, and this was it. Okay, good. Yeah, the next step is creating this vertical column here. And this is an hinge column. So again, I click here on this member, right click, and now I say divide member, graphically in this case. And now I can say, okay, which step do I want to have? In this case, I decide here 0.5. And independent now on the chosen member, I can divide any member, as you can see here. I can divide here this upper beam, the left beam, the right column here, or this one. And you can see here, when I move a little bit along this member, I can see also the division spacing, how it's changed. And we want to divide this now at the length of 4.5 meters. I click here on OK. And this was it. Right click or escape. I close this dialog and I have divide here this member and I get a new node. And now my most favorite function of RFEM is copying via drag and drop. So note, and also remember it when you work with RFEM, use this function. This makes your life really easier. Just select it. Just select the left column. So I draw a selection window, in this case from the right to the left upper corner. So everything within this selection is selected. Then press the Control key on your keyboard, then also the left mouse click, and do it from the left to the right here to the new node and leave it, and you have created this new column here. Good, so easy, really easy. Maybe I can show you the power of this function also, maybe with a great example. Just select everything here. You don't have to do it. Press the Control key. Click here on maybe on the left corner node, and then just easy and simple copying. It's so easy. It makes your life really easy and makes fun. Okay. I make it undo. Just click the Control key and Z, or here also in the symbol bar, undo button. Okay. Good. Now, the next step is to create here the bracing. So the bracing, in order to make it here stable and also to guarantee the stability here, because we will add here some hinges, I will do here this bracing. The bracing has nonlinearities. What does it mean? We will activate only tension forces in this member types, to the member types. First of all, I will create this bracing and then I will explain it to you afterwards. So in order to create here these bracings, we have a very nice function here on tools, and at the menu bar, you can call up here the tools and then go to generate models, members, because we want to create members. Bracing are members. Bracing in cells. And then member type, tension, because normally the bracings get tension forces and we only want to have the tension forces. So we decide to do it like that we do here tension. So the member only get tension and nothing else. So if this member will get any compression forces, then it will fail and it don't have any influence on the structure when calculating the results. So now I have to choose the right cross section. Of course, we have just a small diameter of 20 millimeters. So I create a new cross section here. Take this round or import rolled cross section. I do here this one, RD20, so 20 millimeters. Click on OK. And now you see here on the frame this cross, but only for the upper cell or field. And this is also only the field I can choose for creating my bracing in cells. The other one at the bottom, I can't choose because they aren't closed. So in order to close or to create a cell, we have the possibility to create a virtual line. Just do here, select virtual line in order to close here this right field or right cell. I click on OK, and then we get a new cross. And now we can create this the bracing there. Just select cells. I click here, this cell. I click on OK. Again on OK. And we get here a new cell. Okay, so much to the modeling. Ismail, are there any questions or have you already answered some questions?
So far, so good, Daniel. No questions.
Okay. Because I see there's some questions, but I don't know if you can see it also.
Oh, really?
Take a look to the...
I'm at the chat and I can only see your very first message.
Okay, you have maybe to activate also questions or Fragen.
Oh, yeah. Okay,
and,
yeah, cool.
Can see.
All right, I'll take care of that. Is it possible to get frame from DXF? That's probably a question you could.
Yeah, this is possible. This is possible. You have different options to import anything. First of all, here, import. Here at the menu bar, file, import. You can see all supported interfaces and also the DXF file. And if you want to have it as a background, you can also use here guide objects, visual objects, and here you can use, background layers, and here you can enter any DXF files. Yeah, for example, this is possible. And the other question was, do you use Ctrl+P or Ctrl+C to copy? I use Ctrl+C to copy. Yeah. Okay, good. Okay. Let's continue.
I guess sometimes, because I noticed it and I thought maybe it's only my internet problem, but apparently it's not. I think sometimes, just really sometimes, we don't really see what you're doing, and sometimes your voice, you say things that we don't see. So probably, yeah, there was someone who noticed a bit of a speed problem. So yeah, if that happens again, I'll let you know. But so far, it doesn't seem to be a huge issue.
Okay, sorry for that. I'm really sorry. I don't know how to deal with that. You have to know, in Germany, we don't have the fastest internet connections. So We are sorry for that, but doesn't matter. You will get the recording, and in the recording you will see that my audio is equal to the sequences you see as video, so you can watch it afterwards and everything is fine, I think. Good. So the next step is to create the hinges, the member hinges. And in general, we have member hinges because because the hinges are supposed to the members. So there are also 2 or 3 different ways how to insert different hinges. First of all is to create a type of a hinge. So double click on the left part of this beam. And then create here a new member start. Create new hinge at member start. And here I choose phi y because I want to have a moment hinge, and therefore I don't want to transfer any moments to the other members. So I have to activate here this restraint, and this will allow me to do or to create a member hinge, and therefore I can't transfer any moments. When I want to activate any deformation hinge or the deflection hinge, then I have to activate here UX and UZ. And remember, in this case, this hinge refers to the local member axis. Yeah. So when I want to have a vertical, so I don't want to transfer any vertical loads, so I have to activate UZ. When I don't want to have when I don't want to transfer any axial loads, so in this case normal forces, I have to activate UX. And when I don't want to have activate any moment forces, moments, I have to activate phi y. I can do this also with the shortcuts here. Set rotational release and so on. Okay, good. When you want to add some springs, just enter here any type of spring constant, and then you will get a spring. But in this case, we don't need it. So I click on OK. And now you see here, member start gets this member hinge. And also here and on the left side of this beam, we will see this member hinge because member start is here on the left side. I click on OK and I see it here. And this white dot or node is my member hinge. So the second variation of inserting or creating member hinges is with the help of the Data Navigator again. So go to the left side, open the Data Navigator and scroll to member hinges, open the data tree, and you see here this type of member hinge. In this case, local and yes, this means no, yes. So we activated this at phi, and now right click and assign graphically to members. I click on it. Now you see some additional blue nodes, and these blue nodes shows you where to enter these hinges. So When I move to the middle of one member, I would add the hinges on both ends. When I move a little bit to the right or to the left side, just then I would create this member hinge only on one side of the member. And in this case, I decide for the right side on the middle girder, and then for the upper side of this column here. And then I click on OK. And now you see here these member hinges. Everything fine. Now let's do the nodal supports. Nodal supports, very easy. Just select from the left to the right lower corner, because I only want to select these things which are really in this selection window. So in this case, these 3 nodes. Now I go here to the symbol bar, new nodal support. And now I see here this type of support, hinged. I choose this one. I click on OK, and we see here this fixed support. And now the whole structure is also supported. Okay, maybe a few words to the member hinges. When I do this kind of connection, maybe I have here maybe a cantilever beam, for example. So I divide it here by 1, divide member graphically in the middle. And this is a continuous beam, so hinged. And this sliding in X direction. And now I want to activate here a hinge, because I want to have it statically determined. Then double click member and I activate it. And this is everything you have to do. No additional adding here on the on this side, because this would end to an instability, because you have here too much member hinges, and this would lead to an calculation error of the program. So remember, when you have 3 member hinges on one node and also 3 members which connect on one node, then you have done something wrong, because this isn't possible. And also when you have here maybe any diagonal connection, for example a truss or something like that, and you want to connect this here also with the help of a hinge, then it's very easy. And this one you can delete. Sorry, my fault. Then you have here this member hinge connection. Yeah, this is correct. And when you would have here 3 additional 2 member hinges, then it would be false. So much to the hinges. Okay. Good. Next thing is, what else? Yeah. The next thing is the member types. So when I double click on one of the upper beams there, I see the member type beam. We have also other member types, for example, rigid, rip, truss, tension, compression, and so on. The standard member type is the beam type. This means all internal forces are transferred to other members. So in this case, normal shear forces are transferred from the upper beam to the left and to the right beam. And when you would have, for example, a truss is nothing else than a normal beam type. And at the end, you have two hinges on the left side and on the right side. And then also some non-linear member types like tension, compression, buckling, and cable, and so on. Compression member type is, for example, when you have a member which can only carries compression forces, and the same also for tension loads or tension forces, only tension forces. And we will see it after the calculation, because when some of these bracing gets shorter, so it will get compression forces, then it won't be considered, and the other one is considered because it will get longer, and also there we will see tension forces. Okay, so remember, when two or more members are connected by the member type beam, then all internal forces are transferred from one member to the other. Okay, good. So next step is the adding of loads. Before we do that, we have to create a new load case. In this case, one load case is enough. So I go here to the symbol bar, click here on new load case. I enter any name, doesn't matter, test, and deactivate the self-weight, because the self-weight isn't important for the moment, because I only want the critical load without the self-weight, without the consideration of the self-weight. So I click on OK. And the next thing I do is to add the vertical loads. So for the beam on the top and then in the middle. To do that, I go here again to member load. Don't mix it up with new line load. We come to that later. Remember, member loads really only for members, like here, for frames, holes, everywhere where you see members. And line load only when you deal with surfaces. Yeah, good. So I click here on member. And then I click here, reference to members. And I activate here load parameters. And in this case, I enter here 12.767. So I belong to the inputs of the manual, of the RS Buck manual. And important is the load distribution is uniform. I think that's pretty clear. And then also I relate to the true member length. Yeah, because remember, self-weight always to true member length, snow load to the projected member length in this direction, ZP. And when you have any wind loads and you have an inclined member, you have to refer to the local axis, like this one. Okay, good. ZL, I click on OK, and I choose the beam on the top. Okay, right click I close this function. Okay, and the next tip I give you on the way is repeat the same function again. In this case, just click the return or enter key on your keyboard. I do it. And you will see the same dialog again, new member load. This will help you when you close something and you want to do the same, or you want to change here maybe the parameters. And this is we do now. We change here the parameter to 68.371. Again, I leave the values here like before. I click on OK, choose this one and this one, and this was it. Okay, good. The next step are the horizontal loads. So for the pressure side of the wind, so on the left side, and the suction side on the right side. Now you can see here two members. In order to summarize two or more members to one member, you can use the object set of members. What are set of members? Set of members are a I would call it like a summarization. Sorry, not summarization. Summary of several members, and it helps you to create loads, for example, easier, or to interpret the results easier, also, and also for the design it is very helpful. So how to do that? Just select the lower column or the lower member, press the Control key in order to add an additional column to your selection. Choose the upper column, then right click, and then go to create set of member. And here you can say, okay, left column, click on OK, and now do the same for the right side. Right column. Okay, in order to see it a little bit better, you can change the display model to the wireframe model. And now you see here this set of member with the dotted lines. Good. Now you can see, now I will show you one of the advantages of the set of members when you summarize it. Again, we create a new member load, and now, watch out, we refer to sets of members and enter here a load parameter of 4.32, and we relate to the member length through member length XL. I click on OK, and now I choose the left and the right column. So easy. Now we can easily change also the parameter here on the right side, because this parameter isn't right, no problem. We can change everything afterwards. So double click on the right load, change here the parameter from 4 to 2.7. So for the suction side, kilonewton per meter, and now we have changed it. Good. Now last but not least, the point loads. They come here to the corners and also here to these nodes. So very easy. Select the whole upper beam. Doesn't matter if the beam is they're also selected. And go to new node load. The program recognizes the selected nodes. So it doesn't matter if the beam is also selected. When you enter here new node load, it will only recognize here this on nodes number. Yeah, and here in this case, just enter the value of 40 kilonewton, click on OK. And the same we will do for the middle slab beam, 2.4 kilonewton. Okay, this was everything. And now I think we can start calculating it. Ismail, maybe before we do that, are there maybe any questions which could be important?
Right now, I'm pretty sure there aren't any more questions.
Okay, very fine.
Oh, there's one. Should we assign beam model type for all frame? Well, that depends, right?
Exactly. So it's up to you how you define your structure. You can do it and then assign the member hinges, for example. If you want to have here an hinged connection, then you can add here the hinges. And here, for example, for the bracing, I defined here the bracing because I want to have here this as a additional stability factor. So I added here also the bracing. I hope the question was answered. Thank you. Okay, maybe interesting point is also the dimension. Ismail, do you know the English word for the maso?
Measuring?
Measures. I think measuring is good, yeah. You can do also some measuring, yeah. For example, when you want to measure here the the horizontal distances from the nodes, you can use it. Go here to the symbol bar, click here on new linear dimension, linear, and then you just decide if you want to refer the length, delta x or delta z. I take here, in this case, delta z, and click here this node, this node, this node. Click on OK, and I see here the distance or the measuring, and the same we do for the height. So I choose here delta z, click here this node, and this node, and here we can see also the height. Okay, thank you. Thank you, Daniel. Good. Then let's calculate it in order to see the results. I'm pretty curious, so you can click here on show results. Then only this load case will be calculated, or you can also click here on calculate all. But we only have here one load case, so it doesn't matter which button you will press. So I could calculate all, and then take a look to the results. So first of all, what we are going to see is the deformation. The deformation is shown in these lines. In my opinion, it could be nicer. So I go to the display navigator on the left side, scroll down to the results area, and then go here to deformation, members, and now cross-section colored. And you see here the cross-section colored also with the right panel. The right panel helps you to identify the deformation or the value of the deformation a little bit easier. So red is high deformation, blue nothing. And in order to get rid of this FE lines, you can also go here to type of display, isoband separation lines, and then you see it like here, like that. Okay, take a look to the deformation. Can you remember what I said to the bracing? In this case, you see this one bracing isn't activated because it was touched with compression forces, and when a member type with tension gets any compression forces, then it will fail and it won't be considered for the next iterations in the calculation. And here you can see also the effect of the tension member very good, because it will be longer and therefore we have also tension forces. Yeah, because the deformation goes a little bit to the right side. It got a little bit longer. So here we will get tension forces and do also some plausibility checks. So can it be possible? So we have here this horizontal load, also this vertical load. So is the deformation correct? I would say yes, it is. Also here, it is supported by these columns, this beam here. So I think it's pretty correct. I can also activate here my table. And what I can also recommend you is go to the results and do also here the plausibility checks. So is the sum of loads in X and the sum of loads in Z direction equal to the sum of supports? And if you see no deviation, then you have modeled it in the most cases correct. Yeah. Take a look to the internal forces. Members. We created here hinges, so we hope that we don't see there any moments. And we don't see there any moments because we have here, in this case, my, and this is there, and no moments. Perfect. Here, support moment, I think this is pretty okay. And here, upper beam, also some corner moments. They are the same. This is also important. Same here. Perfect. Take a look to the normal forces, especially in the columns. We will see some high normal forces. I deactivate maybe the loads. And very interesting, the whole structure is determined by compression forces, except that bracing here, this has tension forces. Yeah, because we have here positive normal forces, it's positive, and this is also the reason why it's blue. The other ones are red. And the next plausibility check is compare the acting internal forces with the reacting support forces or support reactions. So activate here the support reactions. Take a look if the vertical support reactions are equal to the normal forces, in this case 219, here 219. Okay, on the right side the same, only in the middle we have a little bit different because we have here this additional vertical, the additional inclined tension force, and this is also the reason why this vertical support force isn't equal to our normal force here. But when you do your components, then it should be the same here. Okay, I think this was everything. Now let's do the stability analysis. Also very interesting. So for the design of different application areas like steel, concrete, timber, and so on, you have to use our add-on modules. You can find the add-on modules again here in the data navigator. Scroll down to add-on modules. Here we find a bunch of add-on modules. The other way to find it is here at the menu bar. Here on add-on modules, you find it here. Okay, and
Daniel, sorry.
Yeah.
Go on. I'll ask the question later.
Okay. Maybe we can do this after the RF stability example, and then we can answer the questions.
Okay, cool.
Right. Good. Click here on RF stability. Open this RF stability analysis. And then it will ask you, okay, for more accurate stability analysis results, you maybe add there's some internal node distribution. I click here on yes. And now I decide here, first of all, what is RF stability because for those who don't know it, because they haven't participated in the first part of this training, RF stability does a stability analysis by the eigenvalue method. So you can see the equivalent lengths, the buckling lengths, also the maximum of critical loads, and in this case the normal forces which a structure can carry, and also some load factors and so on. But I think it will be better when I explain you this example. So how much eigenvalues we want to have? In this case, we want to have 4. We don't need to consider any favorable effects due to tension, just clear compression. Also no initial pre-stress for cables, we don't have these things. But we have to activate maybe the division also for straight members. So click here on edit FE mesh settings. And here we decide to increase the minimum number of member divisions from 2 to 10. I click on OK. And then calculate it. And now we see here the critical load factor and also the magnification factor. So again, what does they say to me? The critical load factor. Critical load factor means that when I have here a critical load factor of 5.8, then I have to multiply all my loads with this factor in order to make this whole structure unstable. When I calculate all my when I calculate the structure according to the theory of second order, if the factor is less than 1, this means that the structural system is unstable. A factor higher than 1 means that the loading from the available axial forces multiplied with this factor results in the system's failure due to buckling. So, and when I hope I'm right, in the Eurocode 3, so steel structures, when you have a critical load factor between 1 and 10, you have to consider the calculation according to the theory of second order. And the magnification factor is determined, this will help you to determine the moment according to the second theory of order. So you calculate your moment with the first order, theory of first order, with that factor, and then you will get your moment of second order. Okay, and here you see also the effective lengths and also the critical loads. So now take a look. This is the first eigenform, or the first buckling shape. So here you see, when you would put more loads to your structure, and you will have the same loads like here. Sorry, this one, you will have the same loads like here. Then the first thing which would fail is this column here. Yeah, so if you would apply a load with a factor of 5.8, then your structure will collapse. The next buckling shape is this global eigen shape. Yeah? This would be the next failure form, and so on. So much to the eigenvectors, eigenforms, buckling shapes, and so on. And now let's take a look to the maybe also to the maximum load. So remember, this member has the number 8. It's like an Euler case 2 because it's a hinged column. Member 8. So how much load can this column carry? No problem. Let's take a look to our stability. We remember it has the number 8. Number 8, eigenvector number 1, 2000 kilonewton. So what happens when we put the load higher than 2000 kilonewton, and when we calculate according to the theory of second order, then the structure will fail because this column will collapse, will buckle in this case. Okay, so much to the stability analysis. So this, yeah, easy and simple frame. Ismail, maybe now we can answer some questions.
Yeah, I tried to answer the past questions, but now I have a general question saying, is it possible to make a stiffness analysis of members as such as shear stiffness, for example? And if so, how is that made in RFEM? Maybe if you could briefly, tell shear stiffness analysis.
I think you mean to see the different stiffness matrices, because honestly I don't understand the question so well.
Same here.
So concerning the shear stiffness, you can consider also the shear stiffness here in the calculation parameters, and normally the presettings are that we consider the shear stiffness of members. So this is a classical Timoshenko beam. Yeah, so we activate also additional this shear stiffness, and we get additional deformation by this activation. And this is more correct in the reality. Yeah, but
and maybe there's another question about getting slightly different results despite following the same steps and applying the same loads. Is there a reason for that? I mean, normally if we have the same parameters, if we're following the exact same steps, and if you're using the default parameters of RFEM, we would all get the same results, but sometimes it depends on whether you're using theory of first order, second order, and those are parameters you might have changed. Maybe that would probably lead to slightly different results, right, Daniel? But other than that, I don't think we should be landing on different results.
Yeah, I agree with you. It could have several reasons for that. It's really difficult to say, okay, which parameters would cause to these differences. I don't know it.
He said, is it due to the mesh size, the version of the software?
But you have here members, so in this case, it doesn't have so big influence.
Yeah.
But maybe go here to results, back here to calculation parameters. Sorry, no, FE mesh settings, and give here the minimum number of member divisions, 10. Maybe it could have an impact on that, but I'm not sure, honestly. Can have several reasons.
Another question is it possible to see the calculation after running the analysis? If by calculation you mean results, then yes. But the calculation itself, can we see the calculation itself, Daniel? Like the steps, calculation, the iterations?
You see the iterations by, let me check a moment. For false window, you can set here the calculation parameters in here under the tab calculation diagrams. Here you can see the increments and iterations. How long does it take in order to find the exact calculation or the exact result? And you can also print this diagram.
Yes, and then it depends on the graph you show and the results. If you want to see certain results, you can always use the different types of
exactly
results that you can see, so you can understand where those values come from. But yeah.
Exactly. Good.
That would be all. Thank you.
That would be all. Yeah, very good. Okay. Then I would say let's jump to the next example, the modeling and loading of this concrete example. So, how does it look like? I will show it to you. You will also get the training manual, no problem. So, what do we have here? We have here this concrete building, and we will model it together. First of all, here this floor plan, the next plans, and yeah, I think this is a very nice and easy example in order to get in touch a little bit with the surfaces and plates and shell theory in RFEM. So let's do this. Just a moment. Yeah, sorry, before I forgot it, I have prepared some questions because we want also that you learn something in this training. So please answer me these questions in order to summarize the learned theory and also the learned knowledge. So I have prepared 3 questions, so please answer them. And I take a sip of water. Okay, please to everyone finish this poll or this question. Okay, I close this, show you the results. And the question was, okay, how are 2 members connected when they have the member type beam? Of course, bending resistance, so I can transfer shear, normal forces and bending moments to the other beams. And therefore the first question is correct. Sorry, the first answer is correct. The next question is this one. Okay, I close this poll, show you the results. Okay, what do we have here? Yeah, 2D systems. So we have our easier and more simpler structure, and therefore some boundary conditions are already blocked or are not visible, and therefore the first answer is correct. So it's true that at the 2D system the deformations and rotations of the boundary conditions are partially blocked. And now the last poll for this round. Okay, again, the results of this question. Okay, what are sets of members? You have to understand the sets of members as a combination of members, so as combined members, but independent of any cross sections. So you can have several cross sections. You don't to have any the same cross section. So you can have maybe for the column, 2 different cross sections for the set of member, so it's independent. So the first answer is correct. Okay, good. So let's continue with the concrete example. So therefore, again, click here on File, click here on New, and this time I decide here for the 3D type of model. Model name, concrete example. Again, choose your folder. And now I take here the Euro code, and the national axis also a Euro code, so from Europe. And I don't create combinations automatically because I want to show it you afterwards. Okay, so again, positive orientation of the global z-axis is downward, and with OK we start this project finally. Good. So 3D, you can see here the work plane, and the big advantage of RFEM is that we can choose here now the different work planes. In this case, I decide for the work plane X, Y, because we want to model now the floor plane, and therefore I change only the view, and I want to look to the Z direction. So I go here to the symbol bar, view in Z direction. And now I will create 5 nodes. The big advantage is that we can also, when I know the coordinates of my nodes, I can do it also very easily with the help of the tables. Of course, we can also import any background plans like DXF files or something like that, but in this case we don't have these kind of things. So we decide to do it here manually with the help of the tables, because I want also to show you how to deal with the tables. And big advantage is when you have already some information or objects with some coordination or any other kind of information, you can also import these tables into RFEM. There's a big advantage. If you prefer maybe working with Excel or something like that, you can also do it here. Okay, so our first node, just go here to the tables. When you don't see the tables, activate it here with the help of the symbol bar, table on off, or here at view table. Okay, good. And then go to the tab nodes here in the area of model data. Click here on node type, and then with the tab key on your keyboard, just jump to the next cells and enter here the first node 0, 0, 0. Okay, then with enter, you will create a new node. Now with the node coordinates, let me take a look. 14, 0, 0. Jump to the next row. In this case, upward, so 0, minus 12, and 0. And then 14, minus 12, and 0. And the last one is 0.5, minus 0.5, and 0. Now you see here the nodes, and these nodes will help us to create now additional nodes, and then we can connect our surface or create our surface. Okay, So next part is create the surface. The surface is really easily done when you click here in the symbol bar and you click here at rectangle surface. The only thing you have to do, just create here the material, concrete C3037, thickness 300 millimeter. No, sorry, the thickness is 200 millimeter. I'm sorry for that. And I click on OK. The slab. So the bottom plane or the bottom slab is 200 millimeters, and then we draw this surface from the left corner to the right lower corner. Good. Yeah. The next thing is copying here these nodes along here, along the X direction. So therefore, very easy, right click on the node, click here, move and copy. And then enter here number of copies, click here 2. And the displacement vector here is in this case 5 meters. So it will copy 5 meters along the X direction. And then again here, move and copy. Again, we need an additional node. So we set here the number of copies to 1. Dx is in this case 3 meters. Click on OK. And now we have it. So now we copy all 4 nodes here, 4 meters to the opposite direction of the Y. So right click, move and copy. The Y is minus because against the Y direction is 4 meters. And the next one is only here, this one. So the second right node, right click, move and copy. And this is also 4 meters. So finally done. Good, very good. So the next step is to create here a semicircular surface. Yeah. And therefore we need here the middle point of this line here. So we have to create an additional node. How to do that? Therefore, we can create here a new node, and we have the possibility to create a node between 2 points. I click here on that possibility, and now I choose 2 points, the right corner here, and now I move 4 meters down, so to the Y coordinate -8 along this right line, and then I click OK because I snap now the grid here, and this node should be divided here, or no, not divided, should be created here in the middle, so 50%, and here also 50%. We can set here also 25%, doesn't make, you can use it how you want it, doesn't matter, but this function is really helpful. In this case, I wanted to have it in the middle, so I decide to do it here with 50%. I click OK, and now we have it here. Very good. So now I can draw my semicircular surface. Therefore, again, I go here to this new rectangular surface, and then you see here this arrow. And when I click on this arrow, I see different variations of surfaces, and I take this semicircle. And now watch out, here again, the same properties, just click on OK. And then on the bottom, the status bar, where you see also the snap, grid, Cartes, snap, and so on, these functions, you see on the absolutely on the left side a kind of command, and there you can see select the center of semicircle. Now I have to select the center of the semicircle, so you see the commands on the left lower corner, and then I draw here this circle, and I have here this semicircle surface. Now I have two different surfaces, and I will copy the whole things to the next level. So this means copy everything. So I draw a selection window of everything. Then right click, move and copy. And now important, number of copies is 1, and the displacement vector is against of the global Z direction, because we want to do it in the height, minus 3.25 meters. I click on OK. And what I did wrong, OK, dy, OK. So, and now I draw a little bit my work plane. Press the control key and the middle mouse wheel. Now we see it here like that. So pretty good, I would say. Okay, now we want to hear an opening, because there we want to imagine some stairs, and this is the reason why we want to do here an opening. And remember, openings are only possible when I have really one surface. And now I want to create here this opening within these two surfaces, and this is not possible in RFEM. Therefore, I have to create one surface. So what I'm gonna do is delete here this line. Just select the line, click on delete on your keyboard, and the surface disappears. No problem. By clicking here again in the symbol bar, surfaces, click here on the arrow, you can select boundary lines in order to create a new surface. Select boundary lines, choose the thickness of 300 millimeters. Again, click on OK, and then you can choose here these boundary lines. They are automatically detected and also selected. And yeah, click on cancel, and you have here this surface as one surface. And now we can draw here this opening. So for openings, just go here to next to the surfaces for openings. Open here with the help of the arrow, new openings. And here in this case, we click on circle. And now we select the center of the circle. This is this one. And now you see the disadvantage of this graphical input, because I can't set the right circle parameter, so the correct radius, because I am in the wrong work plane, so not in the same plane. No problem. Go here to circle parameter and enter the circle parameter of 1.8. Click enter, and this was everything. So easy. Good. Yeah, the next steps are the creation of the walls. How to do that? Remember, every surface needs at least 3 lines as boundary lines for the creation of a surface. And our walls have 4 lines. So we need additional lines here in order to create our walls. So I have to divide my lines in order to get additional nodes. And these nodes helps me afterwards to create my lines vertical to that. Okay, let's do that. First of all, I choose only the first floor or the first slab here in this plane. So I select everything. I click here on visibility by selected objects in the symbol bar. And now I only see this slab. Everything else I can't activate or I can't modify. And if I want that the hidden objects in the background disappear, just right click on the context menu and then deactivate show hidden objects in background, and you will only see this one. Okay, again, activate here view in Z direction, and now we are going to divide our lines. Okay, we see our line direction. You can also change the line direction with the help of reverse line orientation. Then you will see, okay, it will change from that direction to the other one. I will undo it because I refer to this line orientation. So the first division of lines is on the left side. Right click on this line, divide line by distance. Good. I want to divide it from the left corner node, left upper corner node, 3.5 meters away. So I click here on line start, 3.5 meters. I click on OK. And the next division is here, upper line, divide line, also by distance. Now from the right side, 3.5. So 3.5. And now here from the beginning, 5.5. Now let's do the same for the right side. Here, right click, divide line by distance, 2 meters. From the top, so from the end, 2 meters. Perfect. In order to make it also visible for you, I create again here the new linear dimensions. So, perfect. Okay, good. So now I want to cancel my visibility mode so that I can see again my whole structure. So I cancel the visibility mode. I see now also the button slab. And now I can draw my lines. Okay, we create a new line. Just create here new line. And we create the new line from the top to the bottom. Right click and again right click. And now we can easily move and copy these things with the help of our drag and drop function. So just press here, select, press the Control key, select this line, copy it from there to there. And this is what we're gonna do for the next nodes we have already divided or created, sorry. Okay, good. Now we can easily create the walls. For that, again, click here on new plane surface. We are selecting of boundary lines. Select the thickness of 200 millimeters. And select now all lines. The same here. The other side. Then here. And here. So, and now you're wondering why I didn't do that here, but that semicircular surface. I didn't do that because it isn't possible to do plane flats or plane surfaces. And here we have this shape, and therefore we have to use this quadrangle. This is a general four-sided surface, and there it's possible to do this surface. So I click here on, quadrangle, same thickness. I choose here these boundary lines, and with the right click or escape, I cancel the input. Now we add here an additional wall. Again, I select here this wall, press my Control key, via drag and drop, I copy it very easily from there to there. Ready. Good. Okay, the next step are the columns. The columns are done with different cross sections, and therefore I create a new cross section and a new single member. I click here on new single member. And create a new cross section. And we choose here a rectangular cross section. (300 by 300 millimeters), so quadratic cross section, concrete cross section. We leave this material. Looks like that. I click on OK. And this is also the reason why we have created so much nodes before, because now we can easily create here this member or this column. Now again, via drag and drop, this is absolutely my favorite function. I can easily copy it from one node to the other. Now I rotate a little bit my structure in order to select all 4 columns at once. Right click, move and copy. Now I can also select the displacement vector with the help of this nodes. Click here this node and this node. 4 meters, zack. And the same I copy here to that. Okay, fine. I think this was almost everything. Now we will create the window on this side here. Here we want to create a window, so a new additional opening. And when you will do that, you will see it isn't so easy to do that because now we are not in the same working plane. So when you don't have to do it with me now. When you click here on the rectangle and when you want to work here, it's not possible. Even if you change here the work plane to the XZ direction, you can snap here any grids and this wouldn't work. So therefore, we have the possibility to change this origin of our grid and work plane. So here in the symbol bar, we find the set origin of grid and work plane. Click here on OK, and let's choose here this corner. Now we will create new nodes. And now you can refer to the grid origin or to the current coordinate system. In this case, I refer to the grid origin. This is also the reason why the coordinates get this apostrophe here at X, Y, and Z. Current coordinate system would be that coordinate system before. But in this case, grid origin, and I enter here the new coordinates. In this case, 5, 0, minus 2.5. So I click on apply. And this was unfortunately the wrong one. I am sorry. Again. Uh, 1.5, 0, minus 1. Okay, and the coordinate X should be minus 2.5 here, definitely. And here, yeah, it should be 5. Okay, doesn't matter. I think now I know the reason. I am really sorry. Now I know the reason. Yeah, I modeled this wall too short. I'm sorry for that, but I think it's good that this happens to me because now I can show you how you can repair these things. Yeah, so I make this thing undo, this last node. I leave this node because this line should be 5.5 meters. So no problem, really no problem. Look how easy it's to change this. So I will select these nodes, create, say, okay, move and copy. Enter only here so I don't want any copy, so only the movement, and all nodes should move 0.5 meters along the positive X direction, so 0.5. I click on OK. Zack. And this was everything. Now I can create the node again. I'm really sorry for that, but I think now you can see how it's easy also when you do something wrong, how you can change it afterwards. So now coordinate is 50 minus 2.5. I click on apply and now I have it. Fine, absolutely fine. And now I can also very easily create this rectangle, this opening, and now I have it. Perfect. Good. So what is the next step? Maybe before we do the next step, Ismail, are there any questions?
No, but I have a suggestion, if you allow me to say it. Like just in case you don't want to create new nodes, I personally do it using the function, the display options. When you choose not to display surfaces, you could actually select nodes and points in that surface. So if you just hide the surfaces, so when you click there, you wouldn't select the surface, and then add your rectangle and then make the surfaces appear again. That would be an alternative. But I think it's, the good thing about RFEM is there's always at least 3 or 4 different ways to do the same thing. So,
exactly.
Yeah.
Yes, you're completely right, and I agree also with you. There are so much possibilities how to do that in different ways. So choose your favorite way, how you create and model your structures. It's up to you. We offer you different options to do that. So choose your favorite one.
Yeah, maybe if you could like briefly show where it is on the display menu, where to hide members and surfaces on the data navigator, on display.
So you mean here at display? Sorry.
Yeah,
View
yeah,
navigator.
there, display, and
So yeah, display.
yeah,
and you mean this one?
exactly. If you hide surfaces, you wouldn't be seeing the surfaces, so you wouldn't exactly. So you'll be able to select whatever you want to select inside that surface without accidentally hitting the surface itself.
This, yeah, very. Thank you for this suggestion. Yeah, this is very useful. And also maybe another tip: when you don't want to snap any grid points here, just deactivate here, snap the grid, and then you only can snap these points or nodes of the structure. Yeah, and this will make this workflow more fluently. And yeah, but this is also a very nice tip and hint. So you see, you will learn a lot of things here. Okay, good. Yeah, and the next point is, maybe we can leave it like that now, is to create a new line, because now this is also an important point to know, is that every member of RFEM includes lines, but not every line includes members. So let me explain it here. When I select here this column and right click, I see here line and member. When I click here on member, click on edit, I see that the member has included the line 30. The same with the line here, edit, member. Here the line, you see that the line includes the member. And we do it now the same. So when you have a line or something like that, and you want to transform the line into a member, this is possible. And now we do that in this case. So we create a line because we want to do now a downstand beam. So I don't know what that is. I have to, doesn't matter. I create here this, I create now a line from that part to that, and then again to this column. right click, and now I have here this node. I change maybe the web plane again to my YX plane, and also my set of origin to my origin here, or my grid origin to my set of origin. Okay. And now you see here this line, and then select these two lines, right click, edit line, and then press here available, and you can create a new cross section here. And now we will create a new cross section. And now this is also very important. When doing downstand beams, please always use the member type RIP. Yeah. Downstand beams in concrete structures, please always use RIP when you have also this T-beams. Yeah, these T-beams with an integrated surface, then use please RIP. Okay, so before we do here some presettings or some settings, we create our cross section of our downstand beam. This cross section will get let's take me I will take a close look. It also rectangular, the width 200 millimeters and the height 150 millimeters. I click on OK. You can leave it like that. Okay. And now edit member type. And here you can see some settings. So first of all, the position and alignment of our downstand beam. Of course, it should be that the upper edge, so the top edge, should be the same like the bottom edge of our slab. Again, the top edge of our downstand beam should be the same like the bottom edge of the slab. So in this case, on plus side of surface. And what does it mean, this RIP? So for RIPs, the internal forces are determined according to the requirements of concrete design. And the stiffness of a RIP member results from the member height, what we have here, and the surface thickness due to the effective widths, which we determine now here with this integration width. So the internal forces of a RIP member include the member forces and the internal forces of the surface that are integrated from the width B1 and B2. Okay, so this is like in the study of concrete structures, there you learn it too, the similar here. Okay, so what you can do is to determine, first of all, to choose the right surface, in this case, this surface. And now to choose here the width, you can calculate it by yourself, or you can do here a kind of preset. I decide here doing the preset, the length divided by 8, so the span divided by 8. This is in general, in the most cases, correct. And also similar when you would determine it by yourself by hand. And here the same. And also choose here the correct surface. Okay, I click on OK. Then I click on OK again. Now we see it, okay, because we had to choose our surface. The display navigator jumped back to lines and also to surfaces as as activated. And in order to make it for you a little bit more understandable, what we do there, we have here now a kind of eccentricity, because our upper edge of our beam is equal to our lower edge of our surface. In order to make it a little bit more visible, go here to the display navigator, rendering, model, solid model, surfaces, and activate here the field inclusive thickness. And then, maybe this would be better here with the edges. And now you see here, okay, it's absolutely correct defined. Okay, good. Okay, next step. Definition of supports. So on the left side, we have a kind of line support. So therefore, I select here these lines because there we have a kind of line or beam foundation. Right click. And I say edit line, because also from a line or a single node or surface, I can create also supports. So go to the register support and say, okay, available. And we create a new kind of line support. We only want to have the vertical forces. Therefore, deactivate the horizontal conditions and only activate the vertical support conditions. I click on OK. And we see here this vertical line supports. And now the same for the surface supports. So we select our surfaces. Now with the help of our data navigator, because this data navigator enables us also a very good overview about all its existing objects. So I go to surfaces, open the tree here, and I know the first two surfaces, or in this case, the first two planes, are the planes or the surfaces at the bottom. With the pressed Control key, I add another plane or another surface to my selection. Right click, click on Edit, and now you see, okay, surface number 1 and 2 are selected. And then go to support eccentricity, say support available, and now you see here the spring constants you can enter for that. So we want to do it not rigid, so therefore we don't put there any, we don't activate it, so we only enter here any spring constants. So in this case, first of all, we change maybe the units from kilonewton to meganewton, units and decimal places. I click on that and change it here from supports to from kilonewton to meganewton. Okay. And now I enter here the spring constants, 10 meganewton, 10. I jump from cell to cell with the help of the tab key on my keyboard. 50 and also 50. We want to add a nonlinearity, so we select failure if negative context stress in set. And this option corresponds to failure under tension. So that is, if the slab is lifting, so it's going upwards, no more support is provided. and click on OK. Again on OK, and we see here this surface support. Okay, good. Ismail, any questions?
Nope. We don't have any new questions so far.
Okay.
I
Then
mean, there was a question before about the rebar area, but we're waiting until we finish the calculation because it would probably be answered within this example.
Yeah,
so, yeah.
Absolutely. I think it's a good decision. Yeah. Good. Next step is to create the load cases and combinations. So let's go here to new load case. And now we create how much load cases? 6 different load cases. Yeah, 6 different load cases. So first of all, self-weight. I can select here by clicking this arrow, self-weight. The action category is permanent. I leave it like that. And then I create a new one. And this new one is imposed load. Category D. So shopping areas. Now I create an additional load case description, in this case, wind in plus X. Action category is wind. Now I can copy it and only change here from X to Y. And the same thing I do for the imperfections. Again here, imperfection plus X, copy it plus Y. Okay, this is everything. And now, interesting point, and I did it on purpose because now you can create here your own load combinations by defining your own load combinations, but you have also the possibility to create it automatically according to the Eurocode. So doing this afterwards, no problem. Click on OK. Go here to concrete example, go to general data, and then activate here create combinations automatically and choose here load combinations. Click on OK. And now jump back to the load combinations. Go here to load cases and combinations. And now you see here additional tabs like actions, combination expressions, action combinations, and so on. Now we go from every tab to the other. Actions. Here we see the different actions like imposed, wind. We see here also the acting, alternatively, simultaneously, differently. Alternatively means that both load combinations are excluding each other. So load combination 3 with load combination 4 can't be combined together. Yeah. This means alternatively, simultaneously, that they can be combined together. Combination expressions. Now you can see different combination expressions like the ultimate limit state and also the serviceability. For our easy example, we don't need these serviceability states, so I will delete them. Only ultimate limit state is interesting for me. And there I can say, okay, imperfection load cases, because I have also some imperfections. I can set them in a different way. I can say, okay, subject to specific load cases, and say, please only with load cases, imperfection towards plus x, with the wind in plus x, because then it is more critical. So I say, okay, only with load cases, with plus x, I click on OK, and here the same with plus epsilon, I click on OK. Here you can see maybe the design situation. I think this is known from the standard. Here you have for the partial factor for the permanent loads and actions, then for the pre-stressed, then for the variable action, and then the sum of all other variable actions. Jump to the action combinations. There we can see it. Maybe, okay, we have imposed and wind loads, and the difference is that we have one leading action. In this case, this is the wind here. So with a full partial factor of 1.5, and every other actions have the partial factor, of course, also of 1.5, but also the combination factor of 0.7. In this case, for the imposed loads. Okay, to the load combinations. What are load combinations? The load combinations are treated as one load case, which is calculated according to the second order analysis you will find here under the calculation parameters. And this load combination is a combination of all load cases under the consideration of the partial and combination factors to one bigger load case. So for example, we have here combination 6. Yeah, there we have load case 1, load case 2, load case 4, and so on. And the leading one is here in this case the wind. Yeah, and therefore we have here for the imposed load the partial factor of 1.5 times 0.7 equals 1.05. Okay. You can say it, you can see it here also, and so on. Okay, and now let's come to the result combinations. What are result combinations? In a result combination, the maximum and minimum values of internal forces, deformations, support forces, and so on, are determined. So the model is not recalculated, it sums all available, in this case, load combinations into one result combination, and you can see the maximum and the minimum of results. Okay.
Daniel, there's a question. Well, first of all, I hope that answers the part about the details of the calculation, the way you can see it in the load combinations. But there's a new question about the possibility to perform a durability-based design in RFEM. And do we have service life prediction options in RFEM?
Okay, I think this is more when I'm talking about durability, then I refer more to, I think, concrete structures. So yeah, this is possible, but isn't the content of this training. But you can design the durability in the serviceability limit state, for example, here in the concrete add-on modules. Let me check, maybe 1 minute, give me 1 minute maybe, and I will check it. Yeah, if you want to consider durability, and I refer to concrete structures, then you have to use your add-on modules, because the whole design of material design like timber, steel, or concrete design is done here in the add-on modules. And if you want to consider the durability, then you have to use our RF concrete add-on modules. But what is a service life prediction?
And
I don't know.
Allow me to add something to that, because the same person asked about the rebar area and how flexure and shear is calculated. That also goes with, it's also possible to design all these things with RF concrete. And once you calculate your structure with RF concrete, you'll be able to see the entire, like all the details concerning the rebar area for flexure and shear. But
yeah, this is possible.
Service life prediction, I don't think, is there any software that really give you an exact prediction of service life? Like,
any prediction how long
the structure will hold? I don't think that's
I don't know any kind of software what can consider these prediction or can predict, okay, how long can this building exist? I mean,
the software gives you exact informations about the analysis itself and the outcome of it in terms of structural analysis. But in terms of prediction, that would be a question of how long similar structures with similar results are used to last in general. But I don't think it's even accurate to say, like, to let a software give you a certain number to it. Like, the software cannot say this structure will hold 50 years or 100 years. I don't think there's any software that would actually do that, because it's not really an accurate thing to say or to give to clients.
In Germany, we have some standards about how long should be this building should be resistant to all the traffic loads or imposed loads and so on. Then we have some values, like, I don't know, for bridges it should be longer than, I'm not sure, more than 100 years, something like that. But
yes, and based on that, the codes are made, and the values we need in our calculation are determined. So it basically, that's where all the values come from. So I'm guessing if the norm says bridges should resist forces for at least 50 years, then you should interpret from that if you use these values and you get the results, you're gonna have a life prediction, a service life of at least 50 years. That's all we can say, I think.
Exactly. Yeah, I think that is correct. And back to the questions concerning the concrete structures, all the reinforced concrete design you do with our add-on modules, but this will be part of our third student training. Okay, so only 10 minutes left, so I will do it a little bit faster now. I'm sorry for that. Now we have to do our loads. We have created our load cases, and now we have to put it on our structure. I will do it a little bit fast, so sorry, I don't want to bother you with that, that we take a little bit longer. So first of all, imposed loads. Very easy, just select the surfaces here. Surfaces here, choose here, new surface load. New surface load, and you see, okay, the surfaces were added. Magnitude is here in this case I hope I'm right. 5 kilonewton per square meter. Click on OK. The same with the other slab. I click again on the return or enter key in order to do the same command again. Magnitude is here in this case 2. I choose the upper slab, and now let's do this for the wind. I choose here, so for the pressure side, this the surface, and there I have 0.4 kilonewton per square meter, but important now to the sorry, to the global related to true area. And now the difference between member and line loads. When I have line loads, then I activate the loads on lines, not on members, but on lines, and the load react or acts on the surface. So create new line load. In this case, I have here 0.65. And for the suction side, I do the same. So I create here new surface load. But in this case, for the projected area, because we have here this semicircular surface, suction side a little bit lower, 0.25. And here again, line loads 41. Good. So I jump to the next load case. So just click here on that arrow, next load case. Now from the other side, choose the surface load. Projected area. In this case, to the global related Y direction, I click on OK. And for these lines, we do the same. .65. Okay, and now I will show you another move with the help of the tables. You can also create line loads. Very easy. Jump here to loads. Choose here the right load case. And now click here on line loads. Choose the right lines. This one and this one. Click on OK. Force uniform load direction is YL, and the load parameter is in this case 0.41. And you have it here. Very good. Now, last but not least, the imperfections. Also very easily done, because now we can also play with the view navigator a little bit. Personally, one of my favorite things in RFEM is the view navigator. I will show me only the columns. So I go here to the view. I go to members, cross section. I activate them. And now I choose only the cross sections with a cross section of 300 by 300. So very good. I see here the member direction. And now I go here to insert loads imperfections, and I say, okay, graphically. I go here to members. Now, to which axis? In this case, z-axis. I hope it's correct. And I enter here only the inclination, so no precamber, according to Eurocode 2. Here we see the equivalent loads of this inclination. I click on OK. I select all columns here. And I hope they are considered correctly. So I change maybe a little bit the display model in order to see it a little bit better. So imperfections toward X, and they are assigned correctly. So they are showing in the right direction, to the right direction. And the same we do with the Y direction. So again, maybe right click on one of the member. We can see also the local axis of our member. And then we see, okay, when we align or when we are referring to the Y direction, to the local Y direction, then the imperfections are done in the Y direction. So we create a new load, imperfections, graphically Y direction, and choose all columns, and then jump back, cancel our visibility mode, and change also maybe our model, and then we can calculate it. Okay, let's do the calculation. Just press here, calculate all, then all load cases, result combination and load combinations will calculate. So I will do that. And there you see maybe, okay, the load case 4, so the wind loads, where we have the wind loads, have some problems with the convergence, because we have here, because we set here, okay, non-linear surface supports, and therefore it is unstable in this load case. But normally this load case isn't alone, and it's always combined with the self-weight, so it doesn't appear in this case. So let's take a look at this load case. Here where you see the loads and maybe the results, and here you see the deformation, the internal forces of the members, and also the surface results like bending moments, normal forces in the walls here, for example, and also the stresses, strains, contact stresses is very important for your bottom foundation here, and also your support directions here, the line. If you want to maybe an integrated or a distributed line reaction, go here to display, go to results, and then to support directions, smooth distribution, deactivate the actual one, and here you see this smooth distribution. Yeah, I think this was everything. Yeah, maybe one important note is that you can also fly around inside the building. So when you want to impress someone, maybe the architect or your student colleague, something like that, and you want to show him maybe the result, the deformations. By the way, on the right side, you will find always the panel with some display factors like for the deformation, and also this color panel. And now when you want to impress someone and you want to fly around, then press the Shift and the F key, and this will enable the fly mode. Sorry. So now, and now you can fly around. Yeah. When I press the plus button, the camera flies a little bit faster, minus button slower. With the arrows on the keyboard, I control this thing here, and yeah, so much to that. Pretty nice. Good. Yeah, I think this was everything. I'm sorry for the late time, because the questions take sometimes longer, sometimes shorter. But yeah, in general, I think you learned a lot, and you can always watch the recording. We will post it on YouTube where you can see it. And yeah, I think this was quite okay for the beginning, especially for you as students, where you can learn the basic things of RFEM. Good. Ismail, before we do our poll, are there any questions?
There was a last question, but I'm guessing it's well, it's about strengthening and retrofitting. Is it possible to hold on just a second. Yeah, to simulate them in RFEM, simulate FRP strengthening or column jacketing? I'm guessing it is possible, but it's not part of this online training, right, Daniel? We can.
Not at the moment. I have to look it up what column jacketing is. Or do you know maybe the German word for that?
Yeah, I'll look it up.
I'm sorry that I didn't hear about it.
Column jacketing. That must be Säulenummantelung.
So putting the reinforcements
to strengthen the column
along the column, and okay, so the so additional. Okay, interesting. You can do you can do normal design of concrete structures, as well as concrete columns, punching, concrete beams, so and so on. Yeah, this is possible, but I don't know if something like that is possible in RFEM. If you need any other or further assistance with questions like that, please write our support, and we will take a closer look to that, because this is at the moment the questions where I don't know if we can consider that in any kind of ways. I'm sorry.
Yeah, and I just sent the address. It's info@dlubal.com. If you have any further questions. I see a last question. A problem modeling in 3D of simple two-way slab with beams. If I look on the result, well, basically it's about the result being different from the 2D one and the 3D example. I'm guessing the third dimension could have a slight effect on the results, considering columns are 3D objects, and that could affect the results of the calculations. But he said the 2D result is the same in my manual calculations. Well, like we said before, this is where we can't really know what the exact issue is, because we would have to check all the parameters you have changed probably in your software, but there shouldn't be a really big difference in terms of values when you change from a 2D to a 3D structure, except when you have an FEM analysis that adds a certain type of mesh to it that could be different from the 2D structure. Other than that, it should all be lead to the same result and the same interpretation.
Mm-hmm. Yeah, I completely agree with you. So again, for everyone, if you need any assistance, no problem to write our support or to write us a mail, attach your model, yeah, and write us a short description about your issue, and then we will answer you within 2 days. And I think then we will, yeah, then you will be happy.
An important thing, because we're already getting a nice message. Thank you so much for this message. It says this software is really amazing, but I cannot find a complete building design example to see all its features. They asked about the link to all the trainings. Just go to dlubal.com. You'll see under, maybe if you could show it, Daniel,
Of course.
the website, you'll see a list of all the trainings we have in order, in chronological order. You can also search for your online training you want, whether for students or for, you have webinars and online trainings. We have individual trainings for our clients. All sorts of trainings are available for students. They're mostly free, well, entirely free for when it's an online training for students. We have the third part in June 15th. Hopefully you guys are gonna attend that one as well. And we have trainings in all different languages. We have one in Arabic next Thursday on the 20th. You can still register for that. We have ones in English, German, French, basically in all languages. And we invite you to just check it on the website www.dlubal.com. Thank you so much again for attending this online training. It's been a pleasure answering all your questions. Daniel, if you want to add a note to that. And of course, we invite you to download the not only the trial version, but if you're a student, you can actually get full access to the complete pack of RFEM just by uploading your by verifying your that you are a student, and you'll get a license for 6 months until you can validate your license the next semester. It's always semester wise the way we do it, but it's always going to be free for students. And I think that would be also check our videos on our YouTube channel. We always post interesting models on LinkedIn, on Facebook, mostly on LinkedIn. We have a lot of free models to download, so you can try certain things on using RFEM. We upload e-learning videos explaining certain things in structural analysis. I've recently uploaded a video about nodal supports, for example. My colleagues upload a lot of videos. Basically, we're on an everyday pace, right, Daniel? Like there's a lot of videos being uploaded every week about very different subjects concerning structural analysis. It's not just about the software being used by clients. It's also about caring about the clients, what they need to understand so they can use the software in the right way. And for that reason, we decided to provide you with all these videos and all these free trainings so you can become closer and closer to the world of structural analysis.
Yeah, Ismail, I think you put everything perfect in a nutshell. Maybe to conclude it, I can recommend you, especially for you as beginners, also for more advanced RFEM users, visit our website here, Structural Analysis Models to Download, where you can find more than 1,000 downloadable structures, and these structures you can download for free and you can open these structures, structure analysis models in RFEM, and can play a little bit around, see how other engineers or other users model them, and this will help you, especially for the beginning, a lot. And I will put now the link to the chat where you find, okay, I filtered it by scaffoldings, but you can find it also here. Good. Now I have I have 2 questions at last, so I think this would be also good for you as a summary of this training, and then we will end this session. So I think please answer me these questions, and then we can end this training. And yeah. Okay, let's close this. Okay, so remember, when you have learned something in this training, then remember, please, that when dealing with concrete structures and you want to design or to model downstand beams or T-beams, so really these kind of things. Okay, I write it in German, but I think everybody knows what I mean. These things here, yeah, these things, T-beam, something like that. Then please design it, please, according as ribs. Please design it as ribs. So the first answer is correct. Okay, and the last questions, and then I will let you. Then I will let you to the week, to the rest of the week.
In the meantime, I just put links to the list of online trainings, and the second link is to the page where Daniel showed you the models you can download for free. And yeah, if you can check those after the online training. And also just take a look around on the website. There's a lot of different things we provide for students, for basically everyone who just wants to know more about structural models with RFEM and structural analysis in general.
Very good, Ismail. Have you provided this link for everyone or just for this one who asked this question?
I put them as answers to questions, but I sent them to everyone, so I'm hoping everyone just got them.
Perfect. Okay, now I will close this poll, show you the results. So, okay, load combinations combines all load cases under the consideration of the partial and combination factors to one bigger load case. Okay, so we are done. I hope you enjoyed the training. I hope you learned also something, and we are really looking forward to the 3rd training. So please sign up for the 3rd training, and we would be very happy when we would see you there for the 3rd time and also for the last time. And as Ismail says, visit our website, requesting for a student license, start modeling with RFEM.
Follow us on LinkedIn and YouTube. That's really important. And yeah, enjoy the rest of the week.
And enjoy structural analysis. Yeah. So see you soon and stay healthy. Bye-bye.
Bye-bye.